recall that in a vector space, we have that for every element in the vector space, we can multiply by a scalar, right? And we can add two elements in the vector space. If V is in the vector space and W is in the vector space, then the sum is also an element in the vector space. And we can multiply by a scalar, and there are some properties that needs to be satisfied. When we multiply a vector and times a scalar, we get an element in the vector space. This is a precise definition of vector space. Something that is important is that regardless of how these elements looks like, they are going to be called vectors. Then let me write that down. Let's say elements in a vector space are called vectors. Basic examples of vector spaces are like the set of matrices 2 by 2. Say matrices 2 by 2. And in this case, this set is the set of A, B, C, D, such that A, B, C, and D. Let's just work in general with the complex numbers. Our scalars are going to be the complex numbers. Then this is a set, and we can multiply by a scalar, by a complex number, and we get another matrix, and we can add two matrices there, and we get a matrix. Then, for that reason, since this is a vector space, we can say that 2, 1, 4, 3 is a vector. Why? Because this set of matrices is a vector space, and elements in that vector space are called vectors. In general, we have that not only matrices 2 by 2, they form a vector space, but for any m and n, matrices of dimension m by n form a vector space. The most classical example is the Cn, and this can be viewed as the set of column vectors, like let's say A1, A2, An, such that each A sub I is a complex number. Then this is a vector space. Sometimes we abuse the notation and we call Cn the set of rows vectors, like A1, An, such that every A sub I is a complex number. This is also a vector space. Notice that these two can be viewed as particular examples of the set of matrices. These are matrices n by 1, and these are matrices 1 by n. Also, let's do another example. For this example, let's suppose that our scalars are the real numbers. Usually our scalars are going to be either the real numbers or the complex numbers. And let's take this vector, which is vector space, which is the collection of functions from the real numbers to the real numbers, right? Such that f is a function. Then in this case, I can say like f1 of x equal x, right? The function that has this graph. This is an element in V, right? f1 is in V. And in this case, we say that since f1, this function, is an element in V, and V is a vector space, then we call f1 is a vector. Then, as I said before, sometimes vectors, they don't look like just like the regular vectors that we are used to. Notice that if we have a function and we pick a scalar, let's suppose that we pick number 5, then 5 times this vector it would be the function that takes x into 5 times x, right? And if we have the function f2 of x equal to 3x squared, then 2 times f2 of x, this would be the function 6 times x squared, which is also a function. Then when we have a scalar and we multiply it by a function, we get another function, and we can add two functions. In this case, f1 of x plus f2 of x would be x plus 3x squared, which is also a function. Then the collection of all functions is a vector space. Let me show you an example that somehow shows us that our r to the power of n is not so far from being a function, a space of functions. Let's consider this vector space V equal to functions defined from the set 1, 2, 3 to the real number. Then an example here would be like f1, the function that takes 1, 2, 3 into, let's say, a square root of 2, pi, and 5, right? Here we are defining the function. f1 of 1 is the square root of 2, f1 of 2 is pi, and f1 of 3 is 5. Remember that we are just making this up just to provide an example. This is an element here, right? And therefore this function, the whole thing is called a vector. f1 belongs to this vector space, and then f1 is a vector. Let's make up another example. f2, another element in this vector space, 1, 2, 3, and let's say that f of 1 is 3, f of 2 is negative 10, and f of 3 is square root of 10. Then in this case we have f2 is another vector, right? And then we can do the sum of the two functions. We call f3 equal to f1 plus f2. Then this function is given by f3 takes 1, 2, 3 into it takes 1 into a square root of 2 plus 3. It takes 2 into 10 plus pi, and it takes 3 into 5 plus the square root of 10. Then we can define the sum of two functions, and we can also define like a linear combination. What about if we take f4 equal to 7 times f1 plus 3 times f2? Then this is also a vector here because it is a function. f4 is given by the function that takes 1, 2, 3 into 1 goes to 7 times the square root of 2 plus 3 times f of 3, it will be plus 9. It takes 2 into 7 times pi minus 30, and it takes 3 into 5 times 7 is 35 plus 3 square root of 10. Then we can define a linear combination of vectors. We can define the sum of two vectors, and it provides a vector. But what I want you to notice is that this vector space is not so far from being the vector space R3 of column vectors like x, y, z, such that x is a real number, y is a real number, and c is a real number. Let's see, for example, we can think of this vector, right? f1 is a vector, but we can also think about the vector v1 equal to a square root of 2 pi and 5. And we have this is an element here in this vector space, but we have like a correspondence for this one. We can define v2 equal to 3 negative 10 square root of 10. Then it's like the value of the function at 1 give us the first entry, the value of the function at 2 give us the second entry, and the value of the function at 3 give us the third entry. Then, and we can see that when we do this linear combination v1 plus v2, we get the vector which goes with this function. Then essentially there are like as many elements in R3 and in this vector space. This vector space looks very fancy. It looks like very mathematical because it's a set of functions, but it's not much different from this vector space that we are very used to. And having that in mind, when we did the example of this vector space of functions from R to R, such that f is a function, then we can think of this, if we are going to think of this as a vector like this, then this is the vector, the entry that goes with 1, the entry that goes with 2, and the entry that goes with 3. There are like 3 entries here, but in this case, when you think in general as a function, then you can think of this as, if you are thinking of this as a vector, then there is like infinitely many entries, 1 for every real number. Right? Then we have that connection between functions and the usual vector space that we are used to, which is just R3. Another interesting example of a vector space is the set of polynomials of order 1 or less. Let's define this as P such that P is a polynomial. We can think that the coefficients are complex numbers with complex number coefficients such that the degree of P is 1 or less. In general, this polynomial will look like P of x equal to ax plus b, where a and b are complex numbers. A particular example, we have that P1 of x equal 3ix plus 2 plus 4i is an example of an element in P1. Notice that here the coefficients are a equal 3i and b 2 plus 4i. Since this is an element in P1 and P1 is a vector space, then we're going to be calling P1 a vector. We can generalize this example to any n. We can define P sub n equal to the set of polynomials of order n or less. And notice that we can add two polynomials of order n or less, and we get something of order n or less. And in general, we can multiply a polynomial by a number, and we get again a polynomial. Something interesting to point out is that if I define the set of, let's say, polynomials of order 2, this set will fail being a vector space. Then let me just write that. This is not a vector space. And the reason is that one of the conditions to be a vector space is that we can't, when we add two elements in there, when we add two vectors, we're supposed to get a vector in there. Let's say that we have the polynomial here, p1 equal negative 2 x squared plus x minus 1, and p2 of x equal 2x squared plus 3x. Then when we add these two vectors, remember that elements in a vector space are called vectors. When we add p1 plus p2, we get the polynomial for x minus 1, and this is not a polynomial of order 2. It is a polynomial of order 1, then it's not an element in this set. Then this set of polynomial of order 2 is not a vector space. But we can easily check that if we add two polynomials of order n or less, then we get something of order n or less. In the same way that we defined linear combination for vectors, regular vectors, we can define linear combinations for vectors when those vectors are elements in a vector space. Then let's suppose that we have the set of matrices 2 by 3, right? And let's suppose that we have these vectors. I'm going to call it v1 just to remind you that it is a vector. Let's suppose that we have 3, 2, 1, 4, 0, 5, and we have this vector v2 equal to 1, 2, 4, 3, 1, negative 1, and we have the vector v3 equal to 0, 1, 1, 1, negative 1, 2. Then we can define a linear combination of these three vectors in the same way that we did before, like 3 times b1 plus 2 times b2 plus, let's say, negative 1 times b3. This is just a linear combination of b1, b2, b3. And again, we're going to call this number 3, this number 2, and this negative 1, we're going to call that the weights of that linear combination. What do we get here? In this case, we get the matrix 3 times b1 is 9, 6, 3, 12, 0, 15, plus 2 times v2 is 2, 4, 8, 6, 2, negative 2, plus negative times v3 is 0, negative 1, negative 1, negative 1, 1, negative 2. And when we add this, we get another vector, which is the vector 11. 10 minus 1, 9. 11 minus 1, 10. 18, 17. 2, 3. 13 minus 2, 11. Then the linear combination of some vectors in a vector space, they will give us another vector. Very similar than this, we can define the notion of linear independence. And again, linear independence, the definition is that k vectors b1, b2, b3, bk are linearly independent if the only solution of the equation, and let's say x1 b1 plus xk bk equal to the zero vector. Notice that this zero vector depends on the vector space. For example, for the matrices, for matrices 2 by 3, the zero vector would be the matrix 0, 0, 0, 0, 0, 0, right? We are talking about a space of functions, then the zero vector will be the zero functions, and every vector space has its own zero vector. Then we say that k vectors are linearly independent if the only solution of this equation is x1 equals 0, x2 equals 0, and xk equals 0. As an example, let's check if these vectors 1, 2, 3 in this space are linear independent or not. Let me check that. I suppose then the question is here, are v1, v2, and v3 linearly independent? Here this is v1, v2, v3. Then what do? We set up the equation x1 v1 plus x2 v2 plus x3 v3 equal to the zero vector. And then we just solve the left-hand side. When we do the left-hand side, we get that 3x1 plus x2. Then the second entry will be 2x1 plus 2x2 plus x3. The third entry would be, here this is x1 plus 4x2 plus x3. We want this to be the zero vector. Entry 2, 1 would be 4x1. Right? x1 times v1 would be 4x1 plus 3x2 plus x3. The next entry would be x2 minus x3. And the last entry would be 5x1 minus x2 plus 2x3. Then, in order to decide if these three vectors are equal to 0, we need to study this equation. And we realize that to solve this equation is true if and only if the following system of equations is true. Let's say here we have 3x1 plus x2 must be 0, 2x1 plus 2x2 plus x3 must be 0, because two matrices are the same. If each one of its entries are the same, then this must be equal to this. x1 plus 4x2 plus x3 equals 0. Here 4x1 plus 3x2 plus x3 equals 0. Here we have x2 minus x3 equals 0. And finally 5x1 minus x2 plus 2x3 equals 0. And somehow it's very easy to prove that if this, the only way this 1, 2, 3, 4, 5, 6 equations holds true is if x1 and x1 is equal 0, x2 equals 0, and x3 equals 0. If you write the augmented matrix of this system and you do row reduction, then you will see that you end up with the system x1 equals 0, x2 equals 0, x3 equals 0, 0 equals 0, 0 equals 0, and 0 equals 0. And also you can also do it by hand. You can say x2 must be equal to x3, then here you have 3x1 plus x2 equals 0, and here you have 2x1 plus 3x2 equals 0, and these two equations, the only solution for these two equations in terms of x1 and x2 is 0. Then that's the way you prove that some vectors are linearly independent. It's essentially the same type of situation as before. Let me do another example. Let's suppose that we have in the space P3, which are polynomials of order 3 or less. Let's suppose that you have the polynomials x squared minus x plus 1. Let's say this is P1. Notice that this is viewed as a vector. P2 x cubed minus x squared plus 4. And let's say P3 equal to 2 times x3. Let's say minus x squared plus 9. Let's check if these three vectors are linearly independent. And maybe something that is important about polynomials that we're going to use a lot is that if we have a polynomial of the form an x to the n plus an minus 1 x to the n minus 1 plus a1 x plus a sub 0 equal to the 0 polynomial. Then the only way this is true is if a0 equal to a1 equal to a2 equal to an equals 0. Actually, let me just prove this for the case when n is equal 1. Let me just say for n equal 1. Let's suppose that we have a1x plus a0x plus a0 equal to the 0 polynomial. Then this is the quality of two functions. Then if we take x equal to 0, what do we get? If we take x equals 0, then we get a0 must be equal to 0, because this function evaluated at 0 is a0 and the 0 polynomial evaluated at 0 is a0. Now we know that a0 is 0. Then if we take ax1, then we get ax1 equal to the 0 polynomial. But if we take x equal 1, then we will get that on the left hand side, we will get that the function evaluated at 1 is a1, while the function on the right is 0. Then we get that a1 and a0 are equal to 0. But we can prove this in general and have this property. Then let's start showing that these three polynomials, or let's start verifying if these three polynomials are linearly independent. Then we take a linear combination. Maybe here it will be better to write alpha 1 instead of x. Then alpha 1 x squared minus x plus 1 plus alpha 2 x cubed minus x squared plus 4 plus alpha 3 2x cubed minus x squared plus 9 equal to the 0 polynomial, which is 0x cubed plus 0x squared plus 0x plus 0. This is the 0 polynomial in P3. Then let's expand the left hand side. Let's group the coefficients of x squared. For x squared we have, actually for x cubed, there is no contribution of x cubed here, and we have alpha plus 2, we will have alpha 2 plus 2 times alpha 3 times x cubed plus the coefficient of x squared, we will have alpha 1 minus alpha 2 minus alpha 3 x squared plus the coefficient of x minus alpha 1, there is no x here, and there is no x here, alpha 1 times x plus the coefficient, the constant coefficient, the coefficient of the function 1, everything that doesn't have the variable, alpha 1 plus 4 times alpha 2 plus 9 times alpha 3 equal to the zero vector, or the zero polynomial. Then, using this property, we have that this equation is true if alpha 2 plus 2 alpha 3 is equal 0, alpha 1 minus alpha 2 minus alpha 3 is equal 0, negative alpha 1 is equal 0, and the last equation is, let me write it here, alpha 1 plus 4 alpha 2 plus 9 alpha 3 equals 0. Notice that in general when you are checking if some polynomials are linearly independent, most likely you will end up with a homogeneous system. You can write the augmented matrix of this system and do row reduction and find out the solution, but from here we get that alpha 1 is 0. If alpha 1 is 0, then we get that, replacing in these two equations, we get that alpha 2 plus 2 alpha 3 is 0, and alpha 1 minus, we get that, and negative alpha 2 minus alpha 3 is equal 0. Then if we add these two equations, we get that alpha 3 must be 0, and if alpha 1 is 0 and alpha 3 is 0, then we get from here that alpha 2 is 0 as well. Therefore, the polynomials p1, p2, and p3 are linearly independent. And they are linearly independent because the only combination, linear combination that produces the zero vector is the trivial one, is when alpha 1 equals 0, alpha 2 equals 0, and alpha 3 equals 0.